This is section 3.6, inverse functions. Today we are going to be finding the inverse of a function and also proving that two functions are inverses of one another. So this is a slight review of 9091 material, but we are also going to get into some new stuff. So let's first discuss inverses and what a function must be in order to have an inverse. Alright, so here a general definition is that a function must be one-to-one in order to have an inverse. Okay, you might be asking yourself, what does this mean, one-to-one? So I'm going to explain that first, and then we're going to do some tests to determine whether or not a function can have an inverse. Alright, so here I've got a mapping of a function. You can see that each x has exactly one y output. Okay, so this is a function. Now a one-to-one function is a particular type of function. It's a function that, well, it's still a function. So here's a mapping right now of something that's still a function, but hopefully you're noticing also that each y has exactly one x value. So this is called one-to-one because every x has exactly one y, every y has exactly one x. So this is what a one-to-one function is. Now you can test to see if it's a one-to-one function really easily because it needs to pass something called the horizontal line test. So what we're going to be doing is looking at some graphs here. I've got 4 different graphs, and I think I'm going to start with graph number 2 first. So let's take a look at graph 2. I've got an inverse function along with a function. So let's call this first blue graph here, let's call that f. I don't need to define it right now. I'm just trying to graphically show you, a representation here. And then the red, let's make that its inverse. Okay. So if you look at f alone, so kind of ignore the red graph here. If you look at f alone, f is a function for sure because it passes the vertical line test. Now f also has an inverse because it passes the horizontal line test. No matter where I draw that horizontal line, it's only going to cross the graph at one point. So this is a one-to-one function. So f is one-to-one, which is why it has an inverse function. So once you reflect it, you can see how it's reflected over this line y equals x. You can see that this new graph, f inverse here appearing, is also a function because it passes the vertical line test. Okay? Everywhere it passes that vertical line test. So you've got a function, and after you apply a reflection over the line y equals x, it remains a function. So if we go back to our example here, this line, this vertical, or not vertical line, but this line here, this is also going to have, it's one-to-one because it passes the vertical line and horizontal line test, and then once you reflect it, this red graph here of this line also passes the vertical line test. In graph 3, it kind of looks a little confusing. I hope you're seeing how the reflection works here, but if you look at your blue graph, let's call that f, okay, and you reflect it over the line y equals x, it still remains a function, right? This is the reflection of this portion of your graph, and this portion is the reflection of f up here. So this still remains a function, right? Which is why f is one-to-one and has an inverse. Okay? Now, the last picture here, your parabola is a function, right? This is a function. It passes your vertical line test. However, it does not pass the horizontal line test. It's got 2 x inputs for the same y output. So this is not one-to-one. It's a function, but it's not one-to-one. So that's why you're seeing, after you apply a reflection in the line y equals x, you see how this graph of the red graph here, this doesn't pass the vertical line test, meaning it's not a function. So that's why your original function went one-to-one. It does not have an inverse function. Okay, it's the key word here. It's supposed to have an inverse function, and in this case it doesn't because it's not one-to-one. Okay, so hopefully that kind of gives you an idea of what it means to be one-to-one and how to tell if something has an inverse or not. Now, you are going to be asked to prove that two functions are inverses of one another, and you can do this algebraically. Okay, so there's a definition It's an if and only if statement, so hopefully you remember that from geometry, that since it's a definition, it should work both ways. So two functions f and g are inverses of one another if and only if f of g of x equals x and g of f of x equals x. So you have to do two different composition functions, and your output of these should be x. Okay? So let me show you and demonstrate. So we have f of x and g of x defined here. If I'm going to find f of g of x, this is f of 2x plus 8. Now, f of 2x plus 8 is 1/2 times 2x plus 8 minus 4. Right? This part here is my input for x. So when I simplify, I end up with x plus 4 minus 4, and that gives me x. So that's step 1 for proving that these are inverses of one another. Step 2 is now to show that g of f of x also equals x. So let's start with that calculation. The composition of g and f, g of f of x, is g of 1/2 x minus 4. So now I'm going to take my g of x here, 2, and then multiply it by 1/2 x minus 4, and add 8 to that. So again, I'm taking this, and making that the input here for x. Okay, and here I end up with x minus 8 plus 8, which also gives me x. Therefore, because f of g of x equals x and g of f of x equals x, these are inverses of one another. So you will definitely be assessed on your ability to do this. And again, all you need to do is be able to show that the composition of each function both ways equals x. Okay, now I want to talk about the fundamental inverse identity, that for f, which must be a one-to-one function to have an inverse, that when you compose f and its inverse, no matter what you evaluate it at, you're going to get an output that is that same number that you're trying to evaluate it at. And it doesn't matter the order, so if you start with your inverse and you compose that with f, then you end up again right back with the number that you inputted. So, whoops. So this is kind of like the idea, like let's say I take the number 9. If I square root that and then I square it, because these are inverse operations of each other, I get right back to what I inputted, the number 9. It's kind of like the same idea here. So I've got a mapping to kind of show you this as well. Now, this set here represents the domain of f, right? Any element inside here maps in f to an element in your second set over here, which represents the range of f, okay? So you have your domain of f and your range of f. Now, all of the values, however, in here are also within the domain of f inverse. So when you map it back, you end up with your range of f inverse. Okay, this is kind of like a circle here. It's the same idea. You apply your mapping, right? And once you get here, you're mapping it right back to where you started. So, let me erase here really quick. Let's take and break down, let's do this statement here. Okay, so I'm trying to take f inverse composed of f of x, okay, and let's start with the inside here. Well, we know that f of x, right, this is x, f of x goes and travels in this way, and it gets me y. So this is y, that's the output of f of x. Now, if I take f inverse of y, I'm starting here, I'm applying this mapping of f inverse right back to where I started at x. So we just showed one of those identities. And of course you could start it the other direction too. You can start with f inverse of y and go this way and then come right back to it. Okay? Okay, so let's use that idea here, and those identities, in order to solve problems 2 and 3. Okay, so problem number 2 says that m and n are inverses. So I just want to draw the mapping really quick to, again, give you that visual. So let's let this mapping represent M, and here represent N. Okay, so we have an element inside the domain of M, and it's 2. Well, this maps, when you apply M, to 7. Now, when I want to find N of 7, this is now my input, right, for N, and I map right back to 2. So the answer for N of 7 is simply 2. Now that's visually why it works out, but it's, again, coming back to this idea here, okay? If you guys also remember from our section, I think 1.7 notes, we took reflections, and we were talking about, you know, which functions are symmetric. But first I had you reflect the point, I think it was 2, 3, over the line y equals x, and it ended up being the coordinate 3, 2 or something. So, actually it's pretty terrible. It should have been the opposite, my bad. Anyway, what I want you to understand is that the x, y pair turned into yx when you apply that reflection. Okay? So this is kind of the same idea here when you see in point 27. When you have your inverse, then the point 72 should appear on that graph. Okay? So that's why n of 7 is equal to 2. So two different ways of thinking of it. Okay, now for problem 3, it says that you have a function f of x that's 2x cubed minus 3. We're supposed to find the composition of f and f inverse of 4. So we're going to assume two conditions, that f inverse exists, so in other words this is 1 to 1, f inverse exists, and that 4 is within the domain of f inverse. So if I draw out a picture of this kind of mapping, then let's call this f here and f inverse. We're saying that 4 for sure is in the domain of f inverse, which means it had to have been an output of f, right? So anyway, if I take this just straight from the definition, I know that this should equal 4. Okay, this is just the identity that we were just discussing. Okay, now the reason why visually is because whatever, like, so I start with this in the inside, f inverse of 4. Well, f inverse of 4, since it's 1 to 1, goes straight to something. I don't know, let's call it, I don't know, smiley face. Okay, I don't know what the number is or what it's evaluated at, but then I apply f of that input, or I suppose the output from f inverse, now is the input for f, and I get right back to 4. Okay, so it's pretty conceptual, but you just need to understand what the identity actually means and be able to use it. So f inverse, or sorry, f of f inverse of 4 equals 4, just as f inverse of f of 4 would equal 4 as well. Okay, these are fundamental. You need to know that. Okay, on a side note, I want to just say that when you're finding an inverse, which we haven't found yet, we haven't algebraically calculated an inverse yet, but when you do find an inverse, make sure that you realize that f inverse of x does not at all mean 1 over f of x. Okay? That's not what it means, because I know, like, in exponents, students get confused because they know that that's true. They automatically think that, oh, this just means, you know, flip it and make the reciprocal of it. That is not at all what that means. So when you're asked to find an inverse, do not do this. That would not be good. Alright. In problem 4, let's try to use the idea that we were just using f of f inverse of whatever, it doesn't matter, x, should equal x. Okay? Or y, or whatever notation we want to use. Now, if I take a look at this, I'm going to try to just play around with this, and I'm going to notice that if I subtract that 5, get an output here of 2. So f inverse of whatever this is, because I'm trying to solve for x, whatever this actually ends up being, it's supposed to equal 2. Okay? Well, from here, I have the coordinate 2, 10, right? From here, I have the coordinate 2, x minus 2. The reason why is because this is f inverse, this is f, right? We're just going to flip-flop. We have the same value here, and if I know that this is a 1-to-1 function, these y's must be identical. They must be equivalent. So x minus 2 equals 10. So x is 12. That's one way of looking at it. Now, another way of looking at this is to say, using this idea over here, okay? So I'm still going to isolate that f inverse. So f inverse of x minus 2 equals 2. Let's apply f to the composition of that on both sides, okay? Now, this side here, let's apply what we know about this. This is just equal to that input, x minus 2, okay? On the right-hand side, this is f of 2, which I'm given. F of 2 is equal to 10. And I end up with x equals 12. You can also think of this as a mapping as well. I feel like I'm doing these circles all like crazy, but hopefully this is kind of giving you a better visual at least. So I have f and f inverse. What this is saying is that f of 2, so I'm going to put 2 in here as the input, leads me to 10, right? Now, alternatively, let's go back to just this. Oops, there's supposed to be a 2 here. Now, f inverse of something, x minus 2, is supposed to lead me back to 2. Well, whatever I applied has to be this number here. Okay, because it's 1 to 1, 10 maps to only 2, 2 maps only to 10. Right? That's the definition of 1 to 1. So that means that this side here, x minus 2, or not, sorry, not side, this input here, has to equal 10. That's pretty much how we get it, I don't know, 3 different ways. Alright, the last section here is to find, or second to last section, sorry. The second to last section here says to find possible inverses. So I think this is probably the easiest question that you're going to do. There's really no abstract thinking at all involved in this. It's straight up algebraic computation. So to find an inverse, first obviously you need to check to see if it's 1 to 1. Let's assume that this is 1 to 1. Well, you can kind of sketch this in your head and you can hopefully tell that it's 1 to 1 anyhow. But what you do is you use your x and y notation. So I'm going to change that f of x to just a y to make this a little bit easier on myself. And then the next step is really important. You have to actually switch x and y. So I'm going to make this now this function here. Okay. My goal is to solve for y. So I'm going to add the 3 over. I'm going to divide now by 2. And then I'm going to cube root both sides. This is my inverse function. Now instead of leaving this as y though, make sure you replace it with f inverse notation. So this is now f inverse of x equaling the cube root of x plus 3 over 2. So just to go back to that note I was telling you about, remember f inverse of x does not mean 1 over f of x, okay? Because this is clearly showing you that that's not the case. Alright, last portions. Alright, thanks for sticking in there. F of x contains 2 points, 3, -1, and -4, -3. I'm going to actually say it's a line. Let's consider this a line, so because I want you to be able to see the reflection. So we're going to contain, or draw a line that contains those 2 points. So 3, -1, and -4. 1, 2, 3, 4, -3. Alright, so here's my line. And I'm supposed to sketch the inverse of x. So, inverse of f, I'm sorry. Now, from before, remember when we apply that reflection over the y-axis, or the line y equals x, I could draw it in if you need me to, but try to visualize that line being drawn in there. Whoa, it's kind of sloppy. Well, if this is the coordinate, right, 4 maps to -3, well then -3 is supposed to map right back to 4, so you now have the point -3, -4, and -1, 3. So -1, 3, and let's do this in a different color. -3, -4 ends up being, whoops, a little crooked still. But you can see how it's reflected now over this ghetto-looking line here. Let's try to draw it a little bit better. Oh, there's the little thing, sorry. Anyways, you can see that that is the reflection over the line y equals x. Okay, the next one says find f inverse if f of x equals x cubed, and then we're going to also sketch it. So let's first find the inverse of this. So let's replace that f of x with a y. Now we're going to switch the x and the y. And we're going to solve for y by cube rooting both sides. And we have f inverse, oops, I forgot to replace that notation. F inverse of x equals the cube root of x. Now let's say I have absolutely zero idea of how to graph this and I don't know how to even make a table. Well, that's okay, because you do know y equals x cubed. So let's create those points. Okay, this would be at -2, -8, all the way up at 2, 8. This would be the line, or graph, sorry, the curve of y equals x cubed. Now I'm going to apply a reflection, which is going to translate all of these points. Okay, if I translate over the line y equals x, or reflect over that line, then each point, the point 1, 1, now the x and the y switch, so I'm still graphing 1, 1. 0, 0 stays, so that's kind of boring too. Got these points so far. -1, -1 also stays. Pretty boring. But 8, 2, or sorry, 2, 8, and -2, -8 do change. So I end up with 8, 2. I'm going to graph 8, 2. And let's put it like right about there. And -8, -2 would be my other point. Let's put it right about here. And connect. Whoa. Alright. So if I erase now the red, this would be the graph of the cube root of x. Okay? And again, I'm sure you know how to graph it, but I just wanted to do it a little bit quicker. Okay. Thanks for sticking in there. Another long one. Great job. Let's go over any questions you still have, because I have a feeling that this is kind of really, abstract concept, and it's tough to really understand it, especially since I'm just talking to you. You can't really ask me questions as they come up, so make sure you fill out that lesson feedback form. Okay? Good job. Talk to you tomorrow.